Welcome back to the discussion on image transforms. In the last class, I left you with the question that if I have a translation happening as a part of image transform, how could I represent that using a single matrix? Before that, let me now also add to the sources of my slides, Professor Aaron Bobbick's lectures as well, particularly for the slides that were presented in this class. I have taken quite a few from his video lectures here. Okay, so yeah, coming back here, I guess you have tried working it out. So one way we represented it so far is x dash y dash. A simple way of writing that we did is I have a matrix here, then xy. I have x and y here, so I should be having 1 0 0 1 here plus tx ty. That's how a conventional representation, a simple representation could be. Now, I want a single matrix to represent everything. So what could be that matrix here? So mine here is 2 by 2, but you are not. So anyway, this has to be 2 cross. What is that you would take and how is that you could represent it is using a single matrix? That's the question.
So we can have a 2 cross 3 matrix.
Very good. What could be the matrix?
So it will be 1,
Hmm.
0 and tx,
Okay. And
and
then what?
0, 1 and ty,
Very good.
and we'll have x, y and 1.
Very good. Excellent. That's the solution. Okay, this is what I was expecting. And this is equal to, now you could see this is 3 cross 2, right? And that would give you essentially x dash y dash. Is everybody able to, who was that answer, who was telling that answer? I could not see the name here. Can you please?
Pradeep,
Pradeep, very good, Pradeep. That's right. So anyone would like to, does anybody have a question here? This is actually about these image transforms. Now we are looking at just from one perspective, but there are different ways of looking at it, and there are different contexts where you encounter these transforms. In those cases, particularly, there is something called as homogeneous transform or homogeneous vector. That's what they call it. So essentially now, this is exactly what you told the answer is here. 10tx, 01ty, and then of course you have here x bar. So original one is getting, you consider this as x comma y, and one here that would give you x dash comma y dash. There is something called as homogeneous coordinate system. The impacts of it, the interpretations of it will be clear to you to a reasonable extent by the end of this lecture. So for the time being, let's do it mechanically, not although we don't understand its impact to the full extent. Let me pose it as a simple problem here, that suppose I want to get here a 3 by 3 matrix. Okay, I want to get here a 3 by 3 matrix. To that end, I am also okay to just put here 1. Okay, now can you tell me, can you rewrite the stuff and tell me how that would look like?
We just add 001.
10tx,
10
01ty, and
tx,
001.
10 tx, right? That is there. Then here 01 ty. Then what?
001.
Very good. That's all. This is the matrix. From now on, you would use this 3 by 3 matrix for all our purposes. And moving from, okay, so moving from x dash y dash to, okay, x dash y dash 1, and this coordinate is called as uniform coordinate system, right? So then it is this 3 by 3 matrix that we are going to use from now onwards to represent the transformations. These transformations are the ones which bring the given spatial coordinate into the modified coordinate or maps it with the other image. So let me now come back here to this slide. Again, you could see here, this is 0, 0, 1 that got added up here. And you could notice here, earlier it is 2 elements are there. You additionally added one more element here. Okay. And these vectors now, these vectors which are of the length 3 here for a 2D image are referred to as, this one is again this, are referred to as homogeneous vectors, right? By adding 1 here. So essentially, you are representing now a 2D point. Your original point is xy, but you are representing now as a 3D vector. 2D point, you are representing it as a 3D vector, where you additionally have kept 1 here. Okay, this might, and even further generalizing it. Okay, again, please wait for some interpretation to the latter part, but let us just see some intuition for it. Or what we mean here is, for example, I have the original ones are, let me call it as x double prime. Okay, so and y double prime. Okay, that is not the second order derivative or anything that. Okay, so here these points are represented as, finally to compute. So given a 3D vector for you, okay, given a 3D vector for you, how do you compute the 2D point? So that's the question. And what will be done here, given a 3D vector like this, the 2D point can be obtained by doing x double prime, by just dividing the above two values with w prime. So that is equal to x prime by w prime, and similarly y double prime, which is your point essentially, is equal to y prime by w prime. Okay, I'm sure this won't be very clear, and why should we introduce this additional variable of this scaling element of w prime here. But yeah, wait for a moment, okay, and put your full attention here. It should be clear to a large extent to you, right? So as I said, now what we are saying is x prime y prime 1 is equivalent to, you can multiply it with s here, and instead of 1 you have here s, and to get the point from a uniform coordinate, you divide with the third element of your vector, you divide the first two elements with the third element. That is how you move from a 3D vector to a 2D point. The matrix that you are going to get here, so essentially you are applying that transformation on this point here. Okay, you are in the similar lines, you call here the point as x y w, the original point here, and this is called as projective transformation. Whatever you are going to apply here is referred to as projective transformation. Okay, so now it looks like we are doing things in a quite a chaotic way. What could be the reason is, this interpretation is, you need to pay your full attention here on what exactly is happening, or what exactly this kind of application of transformation from a point to the 3D vector would mean. This actually comes from, given a 3D, from a slightly different context. The context being, you are given a 3D object and you are taking projections of it, or in another words, you could think of it as you are simply taking the images of it from different viewpoints, different angles, and so on. So what is it that you would get there given a point x, y, z? So that's a very interesting question. Or to be more focused, let's put as a point as sx comma sy comma s. You could always, any given z, you could write it in that manner, so it doesn't really matter. So the projection of it, if you are taking the projection, so there is a point here in the 3D. Now I'm talking about a 3D point, and there is a ray connecting that to the origin. And if I am taking its projection on a 2D plane, which is at z equal to 1. So this is your z axis. On z equal to 1, that would be equivalent to sx by s comma sy by y. Of course, z equal to 1. Okay, if I were taking its projection on 2, that would have been, or let me put it this way, x comma y comma z, depending on where you are taking projection, this point would vary. So if it is, I'm taking it z equal to 1, this would be equal to x by z comma y by z. In this manner also I could write sy divided by s. You have a 3D point, and when you are getting its projection on 1D plane, then that point would be equal to, if it is xyz, that point will be x by z comma y by z. Okay, this also you could do it in a 3D triangles there by taking it. Okay, but I don't want, I leave it to you. If you are interested, you could do it, but let me just simply draw something in 1D case. Okay, suppose this is equal to okay, this value is, let's say, x naught. Okay, or and this is equal to 1 here, and here it is equal to y naught. Okay, and then what would be this length? So how do you do that here? Say for example, let me call this as y1. What would be that equal to? If I look at so that would be, take the similar triangles here. So y1 by y naught equal to 1 by x naught, and then you will get y1 equal to y naught by x naught. So that's this kind of a similar triangle. I did it in 1D, because 2D I have to draw all those things and do it. So that's the intuition essentially. In other words, let me frame it from a different perspective. A point in 2D, when you are moving it into a 3D, it could in fact represent, if you any of these points, assume that this is from where you are looking at, or this is the angle at which your focal point is there, whatever you may call it. From here, any of these points you might have got. Okay, so that's essentially how you could the kind of interpretation that could be given here is, a point in the image is a ray in projective space. Okay, projection is, you have a 3D object, so you are projecting it into on the 2D plane the very moment you are taking an image of it, because image is 2D. Now depending on it, which distance you are, and what are your camera parameters and everything, right, you are getting a projection of it. So a point in the image is a ray in a projective space. You don't really know, and you do not really perceive the depth there. Any of these points can correspond to this. That's essentially would tell you this. But depending on where you are taking a projection, any of these points would one of those points, it could come there as x y comma 1. Okay, that x y, if you are taking sx sy s, this is x y comma 1. Or else, if you in general, if you call a point xyz for varying values of x, y, and z, this point would be equal to x by z comma y by z. That's the geometric interpretation of using here sx dash sy dash. Yes, because he wants the final point to remain as x dash y dash, so he is in fact writing it this way. Otherwise I could have even written as x dash y dash z dash. If I want to call this point as x double prime and y double prime, then this would be x double prime, as I have written, will be equal to x dash by z dash, y double prime is equal to y dash by z dash. But I would say this kinds of notation is more convenient, because you know clearly that the points are x dash and y dash. There you can just avoid yet another set of x double prime and y double prime by simply using one parameter yes here. If it is just clear to you that you could in fact represent here, you could take x dash y dash w, or x prime y prime w prime, and the point you could get by simply dividing this by prime and this dividing by prime. That's how you move from a 2D point to a 3D vector and vice versa. Okay, you could use any multiplication factor here, S, and you could move from here to here. So maybe here, that's what I would keep here. This, they call it as a they call it as a heterogeneous when they have X and Y. The moment they say homogeneous, this you could move by X comma Y comma 1. You'd be in fact doing some calculations at the end, and where this point gets mapped to, that time you would be getting another value of xy comma w. So from there, to get the point, you would simply doing dividing by this, though these x and y, that would give you the point here. And there is a nice property here, is that scale invariance is there. Suppose when I am getting here, I multiply it with 100. Okay, this with 100, all of them. So lambda, I multiply the whole thing with lambda. Then this would still, since I'm going to divide it, so if I'm multiplying whole thing by a constant vector lambda, it would still remain the same one, which is a very important property. You will be able to figure it out and feel it a little later, importance of it. But I hope anyway you are normalizing it with respect to the factor, so that's having also the property of scale invariance. Is this clear? Is this that instead we are going to use 3 by 3 matrix? This is how you are going to move from a point to a 3D vector, and how we move from a given a 3D vector to a point. If these things are clear, good enough for now. Is that clear? Any
So
questions
what
here?
the third point, sir, lambda times the same
Right,
vector. Could
right.
you just give a small intuitive example right now?
Yeah. See, all it is saying is, suppose you could see here. So I have x. So everything in this vector, I got values of, let's say, x1 equal to. So instead of taking xy w there, I am taking here, for example, lambda times x, lambda times y, lambda times w. Okay, this is what I have as a result of it. Now from this 3D vector, I want to get the point 2D point here. So how do I get the point here? So that would be equal to lambda x by lambda w, lambda y by lambda w, right? So this lambda and lambda getting cancelled. So I would end up with x by w and y by w itself. That is all scale invariance is about. Because anyway, when you are multiplying all the three elements of the vector with the same scale, since you are going to, in order to get the point, anyway you are going to normalize your vector of three elements with the last element, so you would end up with the same point. That's all.
Okay, sir.
Good. So any other questions here? Is that clear?
Can you go back to the slide where you showed a point projection diagram?
This one, right? Yes.
So here, is there any significance or understanding behind the parameter s? What is it signifying, or it is
Okay.
sharing
Yeah,
parameter?
yeah. So yeah, I could have written, as I said, yeah. So they started actually from this, if I am not wrong. Suppose you have a point xy here, and then what are all the values of points in the 3D that gets projected onto this? That's how they posed the problem. So then they say that all points of, yes, I have given you, like, for example, 10, 20. This is the point given to you. Now, what are all the points that could get projected in a 3D space to this point of 10 comma 20? If that is how the question is posed, you could say there that 10 times s, 20 times s, and s. All these points for varying values of s you can take, that would form this ray. All these points in 3D connecting the origin would get projected onto this. That is how the problem is posed.
All
The
those
way,
points will fall on a 2D plane at x, y, comma 1, right?
that's right, that's right. Our matrix from now onwards is a projective, that's referred to as projective transformation of 3 by 3 matrix is what we are going to use from now on. Okay, usually we would use x prime y prime 1 here, except in few spaces where I would explicitly mention that. Okay, so xy, you write it as xy times 1. Okay, that's how you come from a point. So x prime y prime is equal to x plus tx, y plus t. Well, it could have been ty here. This is wrong. You correct it. Ty there. Okay. So then what is the m value in order to get from x comma y to this is, of course, this also is on the your x is now here x y1 here, your matrix is here, and what you have here is x prime y prime 1. You already told this answer anyway. So what I should get, there is no y here, 0, x gets x, then I should get tx here, so that's tx, then y prime equal to y means it's the second element 1 plus ty, so this is ty, there is nothing to do with x, and anyway 1 I should get 0 0 1. That's how I am getting this. Now from now onwards, we revisit all the transformations that we have written earlier, and for the sake of consistency, uniformity, because every time you want to use a single matrix to represent all commonly used standard transformations rather than using for some 2 by 2 and some in a different one. So this from now onwards, our standard format for matrix transformations using representing with matrix is A B C D E F G H I. This is the form that we are going to use it. Okay, this is called as the projective transformation. This is what would happen. Okay, there is some image that we are moved by 2 comma 1. If I give you your tx and ty are 1, this is essentially what it is. And now this is called as transformations in projective geometry. So we will rewrite all the, there are different transformations that you could normally come across. Some of them we have already seen. This is a very, I think this might be from Forsyth and Ponk, this image, if not from Sizelski. Just please check it out. So this is the translation where your x and y had moved. Any guess on what a Euclidean transformation means? From the image, you should be able to say what all do you have in a Euclidean transformation.
Translation and rotation.
That's all. Translation and rotation, if you are giving, that's called as Euclidean. Okay. And what about similarity transformation?
There's also scaling
That's very
along with
good.
it.
Very good. That there is a scaling also. And what about the affine transform? Can you
Shear,
Yes.
translation, and rotation.
And one more is also there.
Scale.
Very good. So all these 4 are there. Translation, rotation, scaling, and shear. If these 4 are there, that's referred to as affine transform. You rarely use this Euclidean. Euclidean is okay, you would use it. Euclidean, there is also another name is there. By any chance, anyone know that name? You normally don't call it by Euclidean transform. There is another name for it. If anybody happen to hear any time, it's referred to as a rigid transform. The name should make sense to you. The object is rigid. It doesn't change its shape. It just rotates. You can rotate it and you can translate it. That's all. So this is also Euclidean transform is also referred to as rigid transform. You would rarely use as such similarity transform. You normally, if you want to go in sequence by increasing the degrees of freedom, you would first do a rigid transform followed by an affine transform. Okay, all put together in, if you have all values for a b c d e f and all, then what you get is a projective transform. Wait for a minute, we will come to that so that we will discuss it in bit more detail. Before that, let's now rewrite the equations that we got earlier in terms of this matrix, okay, which we are referred to as this projective transformation in the 3 by 3 transformation. Let's write that here. Anyways, we are done with the translation. Now rigid body transformation, what should happen? There should be on one side rotation, and on the other side there should be also, you should allow for translation along x and y. Okay, hope you all could see this. So x dash comma y dash equal to x cos theta minus y sin theta, y dash equal to x sin theta plus y cos theta, you are getting here after multiplication. That if you just keep, if I keep all these two 0, right, that is just rotation. Now plus tx for x dash and plus ty for y prime, if you keep that, and this is going to be the matrix representing representing rigid transform. How many parameters are there here to be computed? How many parameters are there? 3 parameters are there. How many were there in the translation? In the earlier translation matrix? How many parameters are to be computed there?
2.
2
Only two.
parameters, right? Correct. Now the another one is scaling. Okay, so you simply multiply the whole stuff everywhere with a. That's all the scaling here means. So you simply have a here. So x dash equal to x cos theta plus y sin theta whole multiplied with a. You are assuming the same scaling in both x and y here. You are not going to make any distinction there, and that's referred to as similarity transform. By the way, let's also look at some properties here. The moment, for example, if you are applying a simple translation, orientations are also of, if you consider, look at the lines that are there in the original object, you do the translation, the orientations are also preserved. The moment you are applying a rotation plus translation, okay, the lengths and areas of the lines are preserved, the angles between the lines are preserved, and of course lines would remain same as lines. Okay, this is very intuitive, you could immediately comprehend that. Similarly, now I am applying this special projective transform, so my r could be something like this. This has moved here, this got rotated here, the whole thing, this object, okay, this whole object is 90 degrees. Now it got some rotation here, or 0 degrees if you consider, this got some rotation, and then the scaling. But you could say, suppose if I have one more object here, the same rotation and everything you applied there, and you consider areas within those objects, the ratio of areas is preserved, the angle between any two lines is preserved, lines would remain same as lines. Next one, affine transform. So now in case of affine transform, as I mentioned, it has both scaling. Scaling means x dash could become a times x. So this has to come. And sharing, sharing, if you recollect, x dash equal to x plus by. That's how you could write. So this b is coming. Then in case of affine transform, x dash can move by a value of, let's say, c. So that gets multiplied. You are getting c here. The same logic holds good for y. And so how many degrees of freedom are there for an affine transform? How many parameters are to be computed for an affine transform?
6.
That's all, 6. So how many pairs of points should I give you in the original image plus transformed image, such that you would be able to find out by what amount it has a scale, what sharing is there, what translation and what rotation are there? How many sets of points should I give you? How many sets of corresponding points? You don't have to establish correspondences for yourself. Say, one thing is, I would say that this and this are corresponding points, I would say. Let's say this and this are corresponding points, I would say. This and this are corresponding points, I would say. Similarly, this and this are corresponding points, I would say. In this manner, how many sets of corresponding points should I give you such that you would be able to compute this transformation matrix?
We can just decompose this matrix into 3 equations. So x dash
Right.
equals
Right. In other words, one set of points is anyway going to give you 2 equations here. So if I give you one set of correspondences, that means I have given you one x dash y dash. Okay. And in terms of x and y, I have given you. So there are already 2 equations from one set of points. So if you have 3 sets of points, you have 6 equations and 6 unknowns. Is that point clear to everyone? All you need is just 3 sets of points to find out the affine transform. Of course, that under there should not be like again all the linear algebra comes into picture here, such that one should not be like, if I give you one point here and another point here, I'm not sure whether you would be able to find out. So mutually exclusive in some sense, where are independent equations you should be getting. Okay, if I want to put it in terms of linear algebra, Okay, let's not go into that part. For those are the minimum points that you require, okay, under certain conditions. So you could always come up with some exception to that. Anyways, so 3 sets of points will give you 6 equations, you could see here, and 6 unknowns. Is that fine? Now I will ask you now a even further simplified question so that most of you would be able to answer it. There is a translation happening from this object to this object. So how many sets of points should I give you in order to compute this matrix that represents a translation? How many sets of points? 1 point should be sufficient, because 1 point if I give you as 110, another point as 222, then there is a shift of these are corresponding points. So 1 has moved to 2. So your tx equal to 1 and your ty equal to 12. That's all. 10 has moved to 22. That's all. Okay. That's the simplified version of this question. Anyways, those things should be clear to you. Okay.
Could you repeat that part again, please?
Yeah, see, I am giving you translation should be having some image. Okay, this image, I told you that this point and this point, one set if I am giving you, assume that it is there at let's say 1 comma 1, assume that it is there at something like 10 comma 20. Okay, then what it means, this one has moved to 10 here, right? So there is a translation in x by 9. This one has moved to 20. So there is a translation in y direction to be 19. That's all. You just need 1 point.
So it was just for computing dx and dy, not the
That's
whole
all.
matrix.
That's all.
Okay. Thank
That
you.
will give you the translation matrix. I'm telling you that there is only translation. So this matrix would be this. If I ask you to write this matrix now, what would happen? In place of tx, you would write 9. Here you would write 19. That's all. That's 109, 01, 19, 001 is the matrix. If you are having in general all these elements, now I leave it to you as an exercise. You do it, and you could actually, I have a slide here that helps you in figuring out what are the degrees of freedom for each of them. You work it out there. You should be able to write these matrices for, if I just give you, there is a scale, there is a shift only in one direction, there is a shear alone, and all these things you should be now able to write on your own. But I'll just focus on another very important aspect of this general projective transform, where I have all these elements A, B, C, D, E, F, G, H, I. So as such, it appears this is one of those who ask questions in computer vision in interviews and all. This is something people would be focusing on. So although we won't be later doing projective transformations on objects, 3D objects, and doing it, but at least I wanted to clarify you this thing so that you have some idea about what it is about. This general projective transformation, people also refer to as homographic transformation. Okay, this is what any 3D object, when you are taking your pictures with a camera at different angles, different tilts, orientations, and everything, then depending on like finding out certain correspondences, you should be able to figure out this is something required when you are merging, you are 3D reconstructing, and all these things. This transformation will come into picture there when you are reconstructing even a 3D from a set of calibrated 2D images. Okay, so coming back here, as we discussed, uh, x prime, y prime, w prime. Okay, let maybe for notationally correctness, you write here x double prime, y double prime. You could always write it as in this manner. So when you are applying a given point, when you are applying this transformation, right, you would, it appear, then what you get in fact, and then you are computing this x double prime and y double prime. This is how after that you could get the shapes where there are still certain properties are preserved. For example, lines would remain as lines, and there is something called as cross ratios. Let's not go into that at this point, that requires more explanation. So look at here, this is a better stuff here. This is, as I mentioned, this is called as homography or general projective transformation, where you have A, B, C, D, E, F, G, H, I. But what is a nice thing that people do is here instead of putting a variable of I here and another unknown parameter I here, they would change it to 1. Okay, this is something in practice done. And notice that this is only going to change your W value. Okay, this is only going to change your W value. And anyway, so later, you, if your original point is x prime y prime, you could write it as wx prime, wy prime, and w. And in this equation, you are modifying just w. So even if you have a different w, since these are all getting multiplied by w and later normalizing it, it doesn't really matter in practice to make this into a constant instead of that making it to an unknown. Of course, you could make it to any constant, but then one looks normalized, so they take it. So the take home message here, which I am giving you, not exactly discussing in detail about homographic transformations, is that the degrees of freedom for a homography transform is 8. Okay, that's all I want you to just make a note here. And somewhat reasonable intuition that I could tell you here, essentially just modify your W value, doesn't really matter. Okay, that's a very very not so precise, but I think serves the purpose. Okay, is that okay? Don't I don't want to dig deep here. Otherwise we have to go into yeah, we will anyway come back to it. It's not, but not I'm not sure to what extent then we have an opportunity to discuss about this homographic transforms degrees of freedom. So this is all I want to mention here. Okay, so these properties of what it preserves is something you could take a look at. We now discussed almost all these transformations. Now see, the in practice you will not get exact. See, the way we are doing is, you have one image, right? From a different viewpoint you have collected the another image, and then you are extracting some feature points here, you are extracting some feature points here, you are making sure to the extent possible that there is a lot of repeatability of key points, even there is a change in the viewpoint, intensities, illuminations, etc. And then you are establishing the correspondences. That correspondences, let's say, be based on the descriptor, you are looking at how close is the vectors, okay, representing it, and that's how you are establishing it. In this whole process, your key point might have moved a little bit than where it should be. In this whole process, you might be getting some key points which were not there in the first image but were there in the second image, and vice versa. So you do not have an ideal situation that we discussed so far. Even if you take, let's say, we discuss it now for an affine transform, degrees of freedom are affine transform 6 degrees of freedom. How many sets of points are required?
3.
3 sets of points are required. Suppose if I have 10 points here, 10 points in the other image, and I have correspondences. So if you are taking every 3 sets of points, for every 3 sets of points, it can so happen that the points which you thought as corresponding points are not really corresponding points. That's one scenario that could happen, because there might not be any correspondence at all. That you might have, when you are assigning it to the closest correspondence, you might have assigned it to wrong point. Second, those might be corresponding points that there, but still there is some error in where that particular point got located for various reasons, right? Because your whole thing is an approximation, you are using histograms, then you are combining the histograms or by 4x4 window. So within that window, if there is some movement there, it is not very sure 100% guaranteed that you would get it exactly at the same point within, well, 4x4 window, or sometimes even more, it could get located. So exactly precise location doesn't happen. So if you have, coming back, 10 points here, 10 points in the other image, key points, and you already know correspondences, if you are taking any 3 of the points, sets of points from these 2 equations, you would get a different solution. So how do you solve this problem? So first of all, don't consider any outliers while you are thinking about how you solve this problem. Okay, then then you introduce an additional complexity of, suppose I have a wrong set of points. There is some point here, x1, x2, x3 are there. Let me put x4 here. Okay, x4 prime, it got mapped. Okay, everything is nicely mapping here. There I had a triangle assume here. The triangle has moved here. Okay, well, okay, this is not a good point. Okay, assume my x4 here. Okay, that has moved here. So these mappings are nice, but notice that if in the first attempt, assume that there is a slight here and there changes, okay, incremental or very small, infinitesimally small changes, then how do you solve it? I give you more points than required. So that's the situation I am giving you. For an affine transform, 3 sets of points are enough. Assume that I give you 10 sets of points. And there are some points where it would be in the surroundings, not exactly the same. So the question for you is, how do you tackle with this? And once you figure out some solution for it, then you include an additional complexity that some points are wrongly mapping there in your whole thing. Now, will the earlier solution work for it? When there are, or to rephrase it slightly differently, when you have some outliers in your problem, so sets of points that we have considered here, outlier means wrong mapping has happened in the very first place. Then how does your algorithm respond or deal with that? Is it going to, I think when it is diverging quite a lot, is your algorithm able to withstand for such outliers? If it is not going to withstand for that, what perhaps could be done? Okay, these are the questions that I would leave you with, and think about them. Okay, I would give you the clue also is least square error. Okay, that's, you should have come across this in other courses also. That's the hint for you. Clarifications regarding anything that we discussed so far.
Yes, sir. About the questions,
Hmm.
so we were asked to identify uh, the correspondence
Hmm.
matrix basically between
Right.
2 points given both the sets of points,
Hmm.
and even possibility of error.
Right. So maybe I will also give you some more hints. Suppose if you have more points, it is like your parameters are, there are 6 parameters, but you have some, let's say 10 points I have given, how many equations would come?
20 equation.
20 equations, right? Now, how do you solve this? This again turns out to be a classical linear algebra problem. You want to find, you have you have 6 variables, you have 20 equations, and now you want to find a solution that is optimal in some sense. So this is exactly turns out to be that. So those who have done are having good understanding of linear algebra will right away will be able to do that. There is something called as least square minimization of so least square problem. This turns out to be a least square problem. So you write yourself those how many equations you take, for example 10, and then you start generalizing that and write equations, and then you tell me how you solve this. Yeah, somebody is saying regression, that's same as the least square problem, right? Yeah, see, least square problem suffers a lot when you have even 3 4 outliers, but they are really outliers. Okay, suppose you have when you have a translation of, let's say, 1 or 2 pixels, if it is showing you some 20 pixels, and if there are such 3 4 guys, it is like taking a class average of all students. And in that average, if there are 3 4 outliers, okay, this assume that I have given computer vision exam very tough, and you want to complain that this paper is very tough, but the moment you have 4 5 guys in the class who scored 30 out of 30, and if I look at an average of the class, that would boost up. Or I could tell you the other way example also. It is just 4 guys are there in class who scored 0, and all the rest scored 25 marks. So but these 4 guys would bring down the whole average and give you a wrong impression of how the overall class is performing. So as such, least squares doesn't take into account, does not figure out who are the outliers. If I could figure out, and if I exclude, I'll do some other study now. In the class, I would first look at distribution and see these guys would score whatever paper I give, they are able to anytime score it. So I should not consider them while looking at how the average class performance is there. And similarly, there are few other guys, how much effort a teacher puts or how much material is given to them, they would they are stable enough to stay where they want. Okay, these two I should exclude them while looking at in general how the class is performing. Okay, because these are really outlier guys. They one guy, however, teacher teaches, these two guys are independent of how the teacher is teaching. Only the other students, if a teacher is teaching well, they will move forward, or else they will come down. Okay, so in similar lines, there could be some correspondences which are wrong, established wrong for some reasons in the whole process. So while your least square method cannot exclude them, there are approaches that does outlier detection and rejection. That's the second approach I wanted you to think about. So how you can do it, just think about it. This anyway, the algorithm is what we are going to discuss. But before we discuss, once you give your full force thought on it, then you will be able to appreciate it very much. So to put it simply, least square problem will be affected when there are outliers. How can I detect outliers? Now I know that I only need these 6 parameters. I have 10 equations. Out of these 10 sets, is there any way I could detect that so and so are outliers? That's one thing. And if you are able to detect, you could always exclude them. So how to detect outliers? That's what the second question can be rephrased as. I'll stop here and see you all on Monday. Bye. Take care.